record me, even though my voice is loud. So I'll put this on. Good afternoon, ladies and gentlemen. I'd like to thank the organisers for inviting me, to Mark and to Peter. When Peter first rang me up and said he wanted to speak at this event, he said it was going to be 10 minutes only, and he wanted an industrialist to talk about a mathematical problem that needs a solution. There are three slight problems with that. One is, although I am an industrialist, that's only for another 2 or 3 weeks. I'm looking to move into academia to look at some new challenges. Secondly, mathematics is definitely my weakest point. My 10-year-old son is extremely good at maths. He is now much better than I am, unfortunately. So my maths level is now classed at that of a 9-year-old, I'm afraid. And the last is that you want me to look tell you about the problems that we have in our company. Well, I still have to have my industrialist hat on, so of course our technology has no problems. It's totally solved. There is nothing for us to do. So thank you very much, and I will. But then I thought, well, I can't speak for less than 20 minutes, or as Peter's probably alluded to, for much longer. There's a lot of exciting technology in what Zebedee does. There are bits that we don't fully understand. They might not be wholly device relevant, but there's certainly some mathematical intriguing possibilities for you to look at. So I thought I'd give you an overview of the company and what we do and what we make, and then pick on a couple of areas where we haven't been into the maths behind the technology. So firstly, I'm going to tell you about who Zebedee are, what we make. In simple terms, it's a liquid crystal display device. It's very traditional, pneumatic, watch-like display device, but the difference is it has a surface relief grating on one of the surfaces that causes the alignment to the liquid crystal. I seem to have the wrong slide there. Oh yeah, sorry, I'll start with who we are. Okay, so who are Zebedee? Basically, we're a spin-out from RSRE Malvern, Derra Kinetic, that formed in 2000. Over the last few years, we've concentrated on shelf-edge labelling for the retail sector. We've now sold over 5 million labels throughout Europe. We are the second fastest growing technology company in Europe according to Deloitte, and we were number 5 in the Sunday Times. And so basically we are taking over the world, if you like, in a new application of displays in the retail sector. We believe it's a $3 billion total market, and we have this unique solution being applied from showing information on tyres to baby wear to standard supermarkets. We spun out of what is now Kinetic. It was RSRE and then Derra in Malvern. We both have the LCD part and our own RF protocol for the communication to the labels. So this is, if you like what our system does, it's a two-way communication system. We have a very simple RF transceiver that communicates to a label, and each of the labels is not like a conventional LCD. It's not like a watch display in the sense that it works with zero power. So it only uses power when it's addressed. It changes the image, as you saw there. And so once the addressing is completed, all the power is removed. And so that way you can have a graphic information and have power from your battery that's built into the unit that lasts for 10 years or more. Only 2% of the power is going into driving the display. The 98% is actually the RF waking up every a few seconds or so to probe whether or not the system is talking to a particular label or not. So because we've got this novel liquid crystal, we've got an ultra power label. Because it's a simple liquid crystal device, it's ultra low cost, which of course is essential for us. So here's the outline of the presentation. First, I'm going to go through how the device works. It's a standard LCD, as I said earlier, but with a grating as the alignment surface in there. It involves surface disclinations which nucleate between two states, which gives us our bistability, and it involves flexoelectric switching of the pneumatic director. So it's not a normal E squared dependence, it's a polar response to switch between the two states. Those last three things are fundamentally different to how a normal LCD would work. We've done some work with Chris Kerr's group at Sheffield Hallam on 2D modelling where we look at the Q tensor, include all of the terms, flexoelectricity, the full viscoelasticity, weak anchoring, etc., and come up with a very complex model that takes a long time to get any results out of. So I'll show you some of those results, but then Nigel Mottram, who's here today, has come up with a much easier, simple 1D model that I'll also show you is pretty accurate in itself when you compare it both to the experiment and to the theory. And then I'll end with this, well, if you know all that and it all works, what are the problems? There's two particular problems that I've not seen mathematical solutions to yet. One is what happens when the gratings are nearly symmetrical, and the other, what is the influence of mobile ionic species on these defects in our device. So the basic idea of the device is to take a surface relief grating. Most liquid crystals are two glass plates with some alignment layer that's flat, put on the two surfaces, a liquid crystal put between the two, and then you switch it by applying a field between those. Roughly speaking, what we've done is modulate one of the surfaces. So there's a metal under here, and then many microns in this direction. This is about 1 micron, 0.8 micron here. So about 5 microns above there's the other electrode, and there's bulk liquid crystal way up there ad infinitum. So our surface features that we've put down have a number of properties. Firstly, they're very deep groove structures. So this is a periodic structure. I'm just showing one peak, if you like, of each for two different states that can be formed. It's very deep. It has a 0.8 micron pitch and a 1.1 micron amplitude, so very deep grating structure, and critically the full width half maximum of this is around about 380 microns. In practice, we actually put a slight blaze on this for reasons that will become apparent later. And the last most critical thing is that we make the liquid crystal, the material, have the right surface energy to make it a homeotropic alignment, i.e. the liquid crystal molecules are normal to the surface. If you take gratings, we've known about gratings for years. If you take a normal grating, you expect the liquid crystal molecules to lie along the grooves rather than go up and down over the grooves, so they're going to just have less elastic deformation if they lie along the grooves. What we're doing is deliberately pointing them up away from the surface chemically and then forcing an elastic deformation into the director field above it. When you then make the grating grooves deep, you have two solutions. There's the one where the director goes over like that and the one where it goes up like that. So you end up at some distance away, roughly half to 1 pitch away from the surface, you end up with a uniform director profile that is either vertically aligned with a high pre-tilt, so that would usually look black if put in a liquid crystal cell, or you end up with a low pre-tilt here and all the molecules go that way but away from the surface, then it's uniform and low pre-tilt. We've got the shape and the anchoring properties just right so that both of these states are equally stable. In this state, what we have is local melting and defect loops or disclination loops of the director field where it's a plus or minus half, plus half defect at the bottom of the grooves and a minus half defect at the top of the grooves. These form loops in this dimension around discriminating between what we call the defect state, which is white, and the continuous state, which is black, which doesn't have those defects in. So the bistability, the fact that the two states are separated by a first order transition, a domain wall transition, comes from the nucleation and movement of these disclination loops across our grating. So a white pixel will have all the grooves for the defects, and then they will form a loop at the end of the pixel, and the next pixel, if it's black, will have no defects in it. So we then put it all together in a standard liquid crystal. A normal liquid crystal is just this. It's 2 glass plates with electrodes patterned to form rows and columns, so you can apply a field by appropriate potential differences on the rows and the columns. Alignment layers on both the surfaces, but one of our surfaces is now our special grating. We put polarizers either side as if it were a watch display, so that in one state, our low pre-tilt surface here forms a twisted pneumatic, so that's just the same as your watch display, and in the other state it's vertical, so there is no twist, and that would be what's called a hybrid aligned pneumatic or hand state. So here's our 2 states, and then in the bulk this is very close to the surface down here, and then in the bulk it either twists around or it goes up from one state to the other. If you've used cross polarizers and the reflector behind them, of course this one looks white and these look black, as I indicate in the top part of the figure. So how do we latch between those 2 states? When you first think of it, you think what we will have is we will have, say, the twisted pneumatic state. We'll put a field on. If delta epsilon of the liquid crystal, the dielectric anisotropy is positive, you'll stand the liquid crystal up, you'll go to black, but you'll never be able to go back to a white state. But if you think about it, because of the submicron texture that we're using, there's a lot of deformation close to the surface of the liquid crystal. And we have areas of high splay and of high bend in the director field only within, in between our grooves, because we're forcing this homeotropic distorted state in both of our states. Now, there's a property of liquid crystals called flexoelectricity, which means that because there's not perfect cylindrical symmetry of the molecules on a molecular scale, as you distort your molecules, you end up with a polarity, a tiny, tiny polarity with respect to the elastic deformation. Now, usually you think of that as so small, it's always screened out by any ions that you'll have. But in our case, it is at the surface where we want a transition between our defects and our non-defect state. So although the flexoelectricity is small, we get voltage switching between the 2 states that is polarity dependent and occurring at quite low voltages. So, okay, I think that's in a missing slide. So basically we therefore have this flexoelectricity. We've got the creation of defects in the display. We've got a transition that occurs between defects forming and defects not forming that requires us to have some kind of anchoring transition right at the surface, and it's clearly a 2-dimensional problem. So there's a lot of new maths, if you like, for us to model and understand the switching of our display. So we went to Chris Kerr's group at Sheffield Hallam, where they used a Q-tensor formulation of the Landau-Degen theory to do a 2D lattice Boltzmann simulation of one of our cells with our grating here and our other surface at the top. And here you see time sections of what happens when we apply a voltage versus time along the top here, and a transition, say, from a non-defect state through to a defect state. And what you're seeing here is how the director field is modulated for different polarities across that transition. I don't fully understand the maths, as I explained earlier, but to deal with the defects, creation and annihilation of the defects where the order parameter goes to 0, right at the top and the bottom of the grating here and here, the Yang-Sheng approach was used. I've got no idea what that means, that's what they used. If you look at the director, oops, well, I was going to show you a picture of the director field itself, so I might have to sketch this up, but basically speaking, What is happening in that transition is we have our grating, we have the liquid crystal trying to follow the grating at the surface when it's in the continuous state. We apply a field, and at the point where the surface is near vertical, you have a bifurcation where one way the director is going this way, the other it's going that way, and hence you will pull out a defect pair that then slides across the surface and ends up at the top and the bottom of the grooves. And that is what this is actually showing you. I actually had pictures of little arrows everywhere, but basically here, a defect's being created here. You can just about see it moving up the surface here as the field separates out and becomes positive, to then favour this state where these defects are getting closer to the points. The negative defect is at the top of the grooves where it's favoured by the local curvature of the surface, and the positive at the bottom of the grooves. When you take the field off, these defects are then held by the local curvature of the surface. So when you model this using that quite sophisticated modelling, you can do things like play around with grating shape. So we look at wider grooves, higher grooves, different pitch grooves, and then actually compare with experimental results. So we've got experimental results being compared with theoretical results here, and you can see we get a good fit to our experimental switching times as a function of the voltages, both from the continuous to the defect state and from the defect to the continuous state on this side. And what that is also showing is that, as we find experimentally, as we make our grating grooves narrower, we actually see a reduction in the voltage. So that's something we'd found experimentally, and it's why we choose a particular pitch with a particular width of grating is all part of that. So it's kind of a good comparison of theory and experiment that's working quite well. And then what we couldn't do cheaply is to then look at lots and lots of different grating structures and work out which way we should go. So we just ran the model a few times and looked, for example, that if we could reduce the pitch of the grating and go from below 800 nanometer pitch down to 500 nanometer pitch or so, we would get increasingly lower voltage behavior, for example. So it's a kind of good use of theory to predict what we can't show experimentally without taking a year to build the cells. We can do the theory within a month or so and get a good prediction of what direction our research or our development needed to take, so that we could recognise that it would be a positive step for us to reduce the pitch of our gratings and move in that direction. Now, everything I've just explained is probably quite complicated because it's this 2D problem with local melting of the liquid crystal to form defects, and it's got flexoelectricity and weak anchoring in there. But what one can do, and what Nigel did very successfully, is to just think of it all as a 1D problem with a threshold between two states. And you don't care what the transition is, it's some domain process, some first order process that nucleates either the low tilt or the high tilt at the two surfaces, and it's mediated by some local surface polarization. The fact that it's flexoelectricity or whatever, that also doesn't particularly matter. It's either a net positive or a net negative polarization at the surfaces. And then when we apply our electric fields across the cell, we're going to do things in the bulk, normally, dielectrically, but principally in terms of what happens at that surface. It's the surface polarization that matters. It's how strongly coupled the surface is to the liquid crystal is to the surface, i.e. its anchoring energy. And so by looking at, just thinking in those two terms, there's only two things you have. You have this surface polarity and you have an anchoring energy for the transition, and you should be able to model it. And what Nigel did is he came up with something that looks like this. This is just taken next step on for a bipolar pulse, and I think Nigel also did something similar to this. But basically that's his expression that is predicting what the latching threshold would look like as a function of a number of simple parameters. So here you have all of the fact that you have different dielectric constants surrounding our grating, because you've got a liquid crystal with its own dielectric properties, and then you've got the electrical properties of the grating, which are different. So that's a simple geometric approach to what the electrical term would be. You then have the anchoring energy, the flexoelectric coefficients, or if you like, how big is the polarization, the surface polarization. You've got some elastic terms, which is the dielectric term coupling to the surface director field close to the surface, that then is helping to drive the flexoelectric polarization. And you also include the viscosities, both the bulk viscosity of the liquid crystal in the grooves, but also a surface viscosity for movement of the domain walls across the surface. And the voltage and cell gap are in there, and tau is just the duration of the electric pulse that you're putting on to induce your change. And so if you then look at that, I can't quite show this, but this is again the 2D model, predictions of what the latching threshold will do as a function of different anchoring energies. So here we have a weak anchoring, and here we have a strong anchoring, and you can see the 2D model works very, very well. But up in the top left hand, you see the comparison between our numerical results and the analytical expression that Nigel derived, and you see again an exceptionally good fit. So although we did 2 or 3 months of this modelling, the basic physics you can understand just using that simple analytical expression. Now it can't do everything. It can't tell you about all the shapes, because the shape terms are just too inaccurate to do that. It's just looking at it electrically. It doesn't have all of the elastic factors relating the relative energies of our two states. But to give us a simple description of what happens in our cells, this tells us that we have quite a simple analytical expression that will work. And why that's of use, for example, is we could do plots like this. You can rearrange the expression to make it a simple linear expression of voltage in cell gap. The intercept here is then related to the anchoring energy. And so if you compare that with a set of experimental results, you get a plot like that. The previous ones were the numerical results. And from that you can then, for the first time, if you like, measure the homeotropic anchoring energy for our material on top of our surface. And it works for both transitions. We get curves, and then we can work out how we can control the voltage of our device simply by changing the chemistry of our surface, which is a really useful technique for us, because we have to get this extremely difficult grating to fabricate and make the same grating on millions of displays. And the way we do that is we copy our grating 100,000 times and use the same copy 100,000 times. That's fine, but the next time we make a grating, it might be slightly different. So although we're then going to be copying it another 100,000 times for another 100,000 displays, it might be slightly different from the first 100,000. And so what we do is we just get one of those 100,000 runs, check its voltage, and then make a recommendation on what anchoring energy to use to correct the voltage back. So all of our devices, all 5 million of them, all work at precisely 15 volts. So you just then plug and play and off you go, having made a correction here. It's quite a clever way of doing it. Theoretically, it's hard to have total control of anchoring energy, but theoretically the 2D model showed that it would become monostable in the D state at too low weakened anchoring energy, which is of interest to us. Obviously what that is saying is we can't go too weak in anchoring energy, else we'll lose this behaviour, we'll lose our two states, and all our displays will just look white and quite even less interesting than they are. So what are the basic problems I'd like to talk to you about? Well, as I said at the beginning, these aren't serious problems. We're happily selling displays, but there are some intriguing things that we found experimentally, and then as a kind of hand-wavy physicist that I am, I start to think about what might be happening, and I think you might therefore have some interesting technical problems you could look at, or mathematical problems that you could look at. The first is about optimizing the pre-tilt. Now we have shown that, I'm talking about pre-tilt, I've got the director is either vertical or it's near horizontal. But we put a slight blaze on so that we get not quite perfect perfectly flat. We have about 5 or 6 degrees pre-tilted from the plane in one of the states and 90 degrees in the other. And what we'd like to be able to do is use 1 or 2 degrees pre-tilt. And the reason for that is a standard liquid crystal display uses 1 to 2 degrees pre-tilt, and that gives it the best looking optical properties. We have found that we have to use 6 to 8 degrees pre-tilt, because as we move our grating towards from blazed to increasingly symmetric, we find that the voltage of operation shoots up very suddenly between 3 and 2 degrees, shoots up to infinity, and you have no latching transition. So as a hand waver, what I think, as I wanted to show earlier, is normally for a quite blazed grating substrate, we will create a defect pair on the steep side, and then these will separate out and then be stabilized by the local surface curvature at the top and the bottom. But as we go to an increasingly symmetric grating, we will have the two sides becoming closer and closer together, and you will have defect pairs nucleated on both sides. And then what must happen is that although you're trying to get one of these defect pairs to stay at the top and the bottom, so say one red one here and one blue one there, what you then have is a competition between these two defects, and the two push each other apart and re-annihilate. So the fact there's two defects here means that defect doesn't like being at this point of surface curvature here, and is pushed back down here where it spontaneously re-annihilates itself. So you never jump into that defect state. You never allow your two defects to get to the top and the bottom of the grooves because of the interference of the other pair of defects. So a technical problem, therefore, is if I want to go to increasingly symmetric gratings to get the pre-tilt closer from 6 down to 2 degrees to get my better optical properties, the question is, what is it that says it's 3 degrees as the point where this very sudden transition to not latching occurs? And there will be properties of the grating and the liquid crystal that we could look at to try to solve that problem. The second problem is more complicated. And again, I don't even know if it's a problem or whether it is an old issue that is quite well known. So I thought I'd bring it up. We're applying a positive field to switch one way or a negative field to switch the other way over our liquid crystal system. Now, no liquid crystal is perfectly dielectric. They will all have mobile ionic species in. And what we have seen for some years in bad systems, if you like, is if we apply too high a field, we can switch back to the wrong state. So if I'm applying say a 20 volt pulse here at 200 microseconds, and I make it 21 volts, it will switch from black to white. But if I keep increasing the voltage up at 40 or 50 volts, it will then, even though it's a positive pulse, it will then go from black back to black. It might intermediately go through white, but it will end up latched back in the black state, i.e. nothing happened. So I only have this operating window here. You might say you'll never apply 40 volts here, but in some systems you want to operate up here, and so your addressing window is getting smaller and smaller for the area of this time and voltage curve that you can use to get it to operate well. So it would be nice to be able to control that addressing window and push this bad transition on both sides out so that you don't see it. Well, simplistically, I come from a ferroelectric liquid crystal background and know all about this. Will just be a very simple issue. It's just about the ions in the system. It's just normal reverse latching. So if you look at our cell, normally this is in the continuous state. You don't have just these directors around. You also have mobile free ions in there. We had our tiny surface polarization, but of course that's then screened out, a device screened by the mobile ions. They'll actually slightly redistribute, so there is no polarization effectively in our cell when before we apply any field. When we apply a field, the first thing that occurs is dielectrically we start to distort the liquid crystal field close to the grating thereby increasing the surface polarization, so it's now bigger than the ionic field. And for a certain polarity, we will then latch and actually switch the sign of the surface polarization to the opposite state and then reorientate the director, so we're now in that other state. Normally, we would then take that field off and it would all relax back to something like this. But if we're applying too high a field, what happens is, although we've latched, the mobile ions will continue to migrate out and then stay at the surface. The ions are much slower than the liquid crystal response or the surface response, and hence they will eventually, because we apply this high voltage for a longer time, they will eventually have a reverse field in the opposite direction to the, acting to reduce our applied field, and we will be in this situation. And so when you take the field off, you're left with an internal field from the ions alone that then switches you back into the wrong state. So conventionally, that's the model that I would think that we should be looking at. It's kind of hand-wavy and simplistic. And when I spoke to the guys at Sheffield Hallam, they said you can't possibly model that because those ions are moving on the timescale of milliseconds, and our transitions are occurring on the timescales of 1 or 2 microseconds. So the timescales mean you can't put both into the same system. So we haven't done any theory on that. I understand that. I'm so used to Peter glaring down at me at the end of a talk. But it just struck me, interestingly, that even for our non-symmetric system, if I'm applying too high an electric field, before my 2 defects have got to the top and the bottom surface, I will start to nucleate a second pair on the shallow side of the grating. And then what we then have is, although these 2 defects get into their latch positions, they're then repelling the defects on the wrong side of the grating into the bulk, which will then swap over onto the surfaces and then go back and annihilate the defects you want to be there. So I have this question, is it just simply ions moving around, or is there a relationship with the amount of blaze that I have in my grating and the grating shape that I have? And so lastly, what I wanted to say is you can have a successful LCD technology which has some unique physics and some unique mathematical problems in it, some of which are outstanding, and still make it a success. And I think that this interaction between ions, very short scale local deformation to liquid crystals, and flexoelectricity on weakly anchored surfaces is something that I hope catches your interest and you want to look at. Thank you very much.
Thank you very much, Cliff. We're really out of time, and
No maths.
there is a session at the end of the day for sort of roundtable discussion, but Nigel's obviously anxious to ask
Your last
something.
idea there, won't you be able to determine whether that's actually happening if you slowly ramp your voltage up? Because really that second defect pair is probably quite a transient effect if you just slowly put a voltage on.
That's a good idea.
The ions
we always tend to look at just the pulses. To me, the obvious way of doing it experimentally was if all we do is just look as a function of blaze. So if we vary the blaze and look to see if the second transition changes, the alternative is adding in ions and see if they change. So you can deliberately try and adjust the threshold. I still believe it is ionic, but it's more why then don't we see the other transition with our pulses when we're operating so close to this. We're at 6 degree pre-tilt, but at 3 degree pre-tilt only, it doesn't work at all. And the only reason for that is because of the symmetry, that you get a bifurcation because of the 2 sets of defects that are competing with each other. So why at 6 degrees don't we see anything associated with that transition? And maybe we do, maybe the form of that curve, which can change in its form. I showed you it like that, but you can get it very vertical and even sometimes over in the other direction, which is highly unusual. Perhaps it's a combination of ions and what's happening with the defects. So it's just goodness knows, and we've not done all the experiments that you could do, but you could think of it theoretically as well. Both approaches have worked in the past, they could work in the future.
Okay, the last question, Sally.
I think you're aware we've done some similar sort of things. So we ended up with a situation where we got the defects coming off the surface at high
Yes.
voltages. I mean, do you think that's likely to happen? Because
Well,
it's certainly happening in our simulation.
That's what I think has to happen here. What I'm trying to show with the orange lines is you can't just stay on the surface, because you're then just going to be repelled down here by the two defects. So you have to be pushed into the bulk of the cell.
Yeah, well, we were getting it to come off the surface anyway,
Yeah.
under certain voltage conditions.
Yes.
And by the way, it shouldn't be that difficult to get the ions in there as well.
Oh yes, I know. Yeah. It's taken them out. Was the
No,
the reason this isn't a problem is
in the
because we don't
simulations that
have
we
many
could
ions
do,
in
we
there.
could probably put the ions in.
Right. Yeah, because you have an adaptive mesh, and you can do the adaptive mesh in time as well as in
Yeah,
space,
exactly.
which is the way to do it. Exactly right, and that's the way forward.
Okay, well, thanks very much indeed, Cliff. That
Okay,
was
thank you.
interesting.